up an example for us to use to hopefully make it make a little bit more sense. This is a 10-acre site, 800 by 540, and we're developing it with 20,000 square feet of buildings, 60,000 square feet of parking and drives, 20,000 square feet of concrete, 2 acres of turf, and the rest of it will be landscape, vegetation, shrubs and trees and things of that nature. Okay. You can see, I don't know, maybe I'll show this in the next slide. There it is. This is my little design. This is representing where the water is leaving the this little curb opening, right? The water is pouring out, and it's going to leave this way. We're actually going to put this water into a swale, and all that water for this entire site's got to leave from that spot. Okay. The site slopes at 2% over non-paved areas and 1% over paved areas. This is very generalized, right? But just trying to give you a sense of what this project might look like. All of the water is to leave the site through a swale to adjacent property. What is the time of concentration? I'm going to pick the furthest point away from the point of concentration, which is my critical point. Can you see this, the furthest point away? So this is the point where my water is going to leave my site, my point of concentration, and my critical point is the furthest point away. Okay, let's assume that everything's kind of sloping this direction. Pick the furthest point away. What surface condition does the water flow over? And so I charted the way the water was going to move across the site. The water was going to move through the landscape area around the building, because that's how I graded it. Okay, your project, your water will move in a way that you designed it. The water is moving, it goes around the building, it enters the parking lot, crosses the parking lot, and then goes into the vegetated swale. So what does it go across? This little pathway goes across 3 different surfaces. What surfaces does it cross? It crosses over 800 feet of landscape and over 150 feet of parking. So let's look at this chart. I said 800 feet of parking area. So, I'm sorry, landscape. So what did I choose? You see how I didn't have anything really to represent the kind of landscape that I thought it was going through. And so I thought it was going through something between bare soil and poor grass. So I chose that little spot. And so my line starts at 800 feet, goes through this condition that I think hits my pivot line. Remember that I said that is a 2% slope for everything that's vegetated. It goes through the 2% and tells me that there's 19 minutes, that the water takes 19 minutes to go across anything vegetated on my site. But I'm not done yet, because I have to also do the paved area, which is 300 feet across paved pivot line through, I did that wrong, it should be through 1%. Through 1%, and it probably would have hit 8 minutes, but mine hit 4 minutes because I did 2%. But be that as it may, I would add these two numbers together, and it would tell me that that was 23 minutes, okay? 19 plus 4 is 23 minutes. It's raining, it takes 23 minutes for water to run from the furthest point to the point of concentration, because the chart told me. Okay. Now that we know the time of concentration is 23, now we can find I. We go to this chart now, and we say, well, the storm is going to last 23 minutes. I take my line straight up, and I go to line 25. Why line 25?
That's for a swale.
Because it's for a swale. Remember, swales are designed in 25-year storms. So I hit from 23, hit that line, and I bounce over from that pivot line, and it's 3.5. So my storm intensity is 3.5 inches per hour. So I know I. And now I have to do a calculation for C and A for every surface on this plan. Now that I know the I value is consistent across this site, across this watershed. And so I have to do the buildings, the parking, the concrete, the turf, the vegetated areas. Why are these all divided out like this? Because they all have different runoff coefficients. Remember I said 20,000 square feet of buildings, blah, blah, blah. And so I have to do this, okay? So let's look at these together. The Q for my building is 0.9. 0.9 is the runoff coefficient for buildings, for roof, remember. Times 3.5. Why 3.5? That's my I, that's my storm intensity, times 0.459 acres. I converted my square footage of buildings into acres, okay? And that's gonna equal something. My 60,000 square feet of parking has a has a coefficient of runoff of 0.8 times 3.5. Again, the storm intensity didn't change in this watershed. 60,000 is 1.38 acres. Okay, so I do that for every single surface in my watershed. And then I do the calculation. You can see here that I get 1.45 cubic feet per second coming off the top of my building during this 25-year storm. I get 2.1 cubic feet per second flowing off of my grass, my turf area, in this 25 years. If I add all this together, I get 18.84 cubic feet per second, arriving at my critical point, which, by the way, is 7.5 gallons of water per second. So we would then size the drain inlet or the swale or the culvert to handle 18.84 cubic feet per second. Okay, that's the watershed part of this whole project. How much water comes off our site? That's all we just did. How much water are we talking about? Okay, we got 18.84. Part 2. This water is moving into a swale. Remember we did swales at the beginning of the semester? We were just like showing where they go, and you guys were like, this doesn't feel right. This isn't right. How big is that swale actually, and how do I actually draw that swale correctly? Okay, that's what we're going to do now. After having determined the runoff, sizing a swale is started by using what we call the continuity equation. That's our next piece, is Q equals VA. Q equals VA. This is going to give us an idea of how big the swale has to be to handle the amount of water we're going to try to put into it. Q equals VA is this. Q should be familiar from our previous equation. It's still the same CFS, it's the same. Velocity, how fast is the water moving inside the swale? And then A is the cross-sectional area of the swale. How deep and how wide is the swale? Okay, that's the cross-sectional area. Velocity is determined basically on the surface of the swale. We don't want to run water, these are maximum velocities, we don't want to run water so fast across these surfaces that we erode them. So we try to keep our numbers below these numbers. So if I was putting water across a gravel surface, I would max out at 6 feet per second. I don't want to go anything faster than that. Grass, I could do 5 feet per second before I start to erode the dirt under the grass. If you're lower than this, it's fine, right? If you're at 2 feet per second on grass, it's totally fine. Okay, so let's think about our example. We're just do the Q equals VA thing here. We have 18.84, we know is our Q already from our previous example. And then the question is what should we use for V, right? If we look back at our little thing here. So we could say that we want our V to be 2, 5, 6. It depends on what the surface material is of that swale. It doesn't tell us in the example what it is. We could use any number we want to. We could use something less than 5 because it might be grassy. So let's do that. Let's use 4, 3, 2. It doesn't matter. So then we're going to solve for A in this particular equation. Okay, so if I put in V, if I put 2 in for V, then my cross-sectional area has to be 18.84 divided by 2. If I put 4 in, the cross-sectional area has to be 18.84 divided by 4. I don't have my calculator. Here it is. 18.84 divided by 4. 4.71. So that means I need to have a swale with a cross-sectional area that area right there needs to be 4.71 square feet. It doesn't, it's not telling me how wide it has to be or how deep it has to be. It just has to be 4.71 square feet. So you could go and start to, design one and say, well, I want it to be 3 feet wide. Well, then how deep is it then if it's 3 feet wide? Okay, just you have to do the math on that. To do it. .57. So if I decided that I wanted this to be 3 feet wide, it would have to be 1.57 feet deep. So the cross-sectional area could be 4.7. Any questions on that?
So it's not just the width, the whole area that we're having? Just gonna be both depth and the width?
That's right. To get cross-sectional area, it's the width times the depth.
It's cross-section across the section, not the plan.
Cross-section across.
Like in the plan, if you have a retention, a swale,
Yeah.
so you're not calculating that cross-section. It's actually in the section.
That's right. So this section would be, there's a swale running along there, and I'm cutting a section across that swale, and that's what that looks like. Right? So there's a bunch of those sections all the way down that particular swale design. Would you know that we're not done? So if you think about it, so what we just did is we found that for our swale, it had to be that big, 4.7 at the, what did we decide? 2 feet per second, right? At 2 feet per second. It has to be that big. What does that not take into consideration? The Q equals VA didn't tell us anything about how, what the slope of that swale was. Didn't tell us anything about what the condition of that swale was. So there's another equation we use on top of this. This gets us close, gets us in the ballpark, but we have to use the Manning formula to actually test the validity of the swale that we just designed. Okay, so let's try that. The second part of sizing a swale is to test the velocity, width, slope, and roughness, and this thing we call hydraulic radius, using the Manning formula. There it is. Again, somebody just made this thing up, and it works like magic. Okay? Let's dissect this Manning formula. V equals 1.486 over n times r to the 0.67 times s to the 0.5 power. V is velocity, feet per second. N is something we call the coefficient of roughness of the swale surface. R is the hydraulic radius, and S is the slope of the swale. Coefficient of roughness is the one you probably, well, actually, coefficient of roughness as well as the hydraulic radius might be unfamiliar. So let's look at those two. The coefficient of roughness, here's the roughness. If a swale is concrete, it has a roughness of 0.013. Did you know that? I didn't know that. How would I know that?
Everybody knows that.
Grass, 0.04. 0.040 for some reason. 0.04. Heavy brush, 0.075. What's happening here is the coefficient of roughness is increasing as it gets rougher, so it's slowing the water down, basically. In our example over there, I think we're going to do grass for fun. Okay. The hydraulic radius is do you want me to go back?
No, it's okay.
You sure?
I can go back, it's fine. I can go back and look at it later.
Just write it down.
Grass.
Or take a picture of it.
Okay.
The slides are on canvas.
It's too hard to find.
Is it
Be
really?
nice to her.
actually nice if you label them.
Oh, shots fired.
Oh, yeah. The label is perfect for me, so it's my 13 collection. That's all I need to
I
know.
like it. It's like, feels like a badass.
Well, you don't know what 13 is.
Come on. 13. Okay, so hydraulic radius, this is looking at the cross-sectional area divided by something called a wetted perimeter. Okay, why? I don't know. So we're going to use this R hydraulic radius. So here's our example over here of a swale. It has 4.71 square feet cross-sectional area. And then the wetted perimeter is, looking for blue. I'm going to use blue. Here we go. This surface plus that surface is the wetted perimeter. Okay. How wide are those things? Well, it'd be really easy if we had this in AutoCAD, we could just measure it, right? We could measure each of those surfaces. Since we don't have that, we have to do this other thing where we go,
Not that again.
yeah.
Come on. Making it up, man.
So in AutoCAD, trust me, in AutoCAD it's going to be much, much easier. Just for our purposes, I'll show you how to, what we're doing here. We can just totally simplify this for today. What would I be doing is I would say, well, the bottom is 3 feet wide, right? Because that was the number that we used, 3 feet times the height. The height of this swale is 1.57. So that becomes the B value for this triangle, right? And this is the A value for that triangle. So then I have to calculate C squared, A squared plus B squared equals C squred. That's the length of the line. You guys remember this?
Come on.
Times 2?
Yeah.
No?
No, yeah. It's like a sick joke.
For today, let's simplify it. Let's say that this is 4.7 plus 1.5 and 1.5, just so we can make it easy on ourselves. Is that okay? So my wetted perimeter in this case would be 7.7 linear feet, right? 7.7. Did you miss how I got there?
I did, can you redo it?
No.
They're over here.
If I add those surfaces together, if I go the bottom was 3 feet wide, if I do those two sides at 1.5, I'm sorry, it's 7 feet wide. I just added it up. The bottom was at 3 feet. This is at 1.5, and that's it. 3, 1, that's 6. 6 feet. Yeah. Thank you for asking. Thank you.
What does that say?
6.
Okay, this is being recorded, so this is, yeah. 6, the devil's number.
It's
All right,
6.
cool.
6. 3 plus 1.5 plus 1.5 is 6. Okay. Cross-sectional area was 4.7 divided by 6. .78. R equals 0.78 in this example.
I don't know how he got me.
What about the slope? What was the slope we were using for our site? It was 2%, okay? Way back when, beginning of this project, we said it was 2%. Okay, so now I have to design a swale that's carrying 18.84 cubic feet per second, across a 2% slope. So I'm gonna plug all those numbers into this equation. I don't know if I did this. No, I didn't. Maybe I did. No, I didn't. I want to do it all together. It'd be fun. Okay. So instead, we're gonna check. So now that we have our numbers that we need to put in here, what we're looking for is the velocity v to not exceed 5. Remember, 5 was the number where my site actually starts to erode, my grassy swale. So I want this v not to equal 5. If I take 1.486 and divide it by n, which is gonna be 0.04 because of our coefficient of roughness for the grass. I can do that. 1.486 divided by 0.04. 37.15. Times our hydraulic radius we just found was 0.78 to the 0.67 power times my slope, which is 2%, 0.02 at the 0.5 power.
And now we know when it fails us on there.
Yeah.
The heavy gravity.
Don't you get the 0.78 again,
That was my hydraulic radius over here, which
Oh.
was the cross-sectional area, 4.7, divided by the wetted perimeter.
sorry?
You remember that?
Yes, so we had this before.
Yeah, yeah.
The R one.
Yeah, the R is the hydraulic radius, that's the thing we just went through, is the hydraulic radius over there. Okay. So now that we have it, we're gonna take
0.78.
That's 0.84 by my math. 0.02 to the 0.5 power. 0.14. And that's all times 37.15. Okay, let me try. 37.15 times. This all equals 4.47. Is it allowed? Okay, so based on Manning formula, the swell that we designed over there is moving water at 4.47 feet per second. Remember, our grassy swell can only go maxes out at 5. So our swell design over there checks out. We can use it. Good? You just gotta do that.
Oh, that's it?
That's it. You just gotta do that.
Wow. Why do you say that?
You go through it again.
It's recorded, Evan.
Mic drop.
Yeah.
We have a question.
Okay, hold on, let me see. Is it affecting for a second? Yes, okay, good. Question, yeah.
So if our number does not check out, then it's about 5 per second.
Yes.
So what can we do?
In that case, you are redesigning that swale, so make it bigger. Yeah.
Another
Two
question.
sides.
Yeah.
So, this lecture now in, the width that we had to have like over 25 feet, just to give that maximum 25 feet.
Oh, from your building
Yes.
system that we're talking about, yeah.
So, is that still, like, can we still reference on that?
Sure.
Or are we still like having everything calculated with all of these formulas?
Okay, so this is good because the example we're gonna do, the worksheet we're gonna do, is going to kind of play off what you're talking about. It's like, where do I locate the swale, right? And then the size of the swale is a part of that now, right? So you have both, how far away do I wanna be from something, as well as how deep is the swale, okay? So both of those, I think, will be in that worksheet. So we'll try it together, okay? Yeah,
So if I calculate my swale off of that number we got earlier, the 4.71.
yeah.
Then it should check out later on, right?
It should, it just depends on the coefficient of roughness as well as the slope that you're working at. So imagine, like, if we would've went to 10% slope instead